by Johan Mazel. It's a joint work with Romain Fontunier from IG Research Lab and with Kensuke Fukuda from NII Second Line in Japan. And Johan Mazel is currently with ANSSI. ANSSI is the French National Information System Security Agency. So he's been there for a few months, since December 2016, and before that he was postdoc at NII with Kensuke Fukuda. And he's done his PhD at l'ACNRS in France with Philippe Orezarski. So Johan is mainly interested in network security, and the talk will be about profiling internet scanners with historical view on that question.
So thank you very much for the introduction. So a bit of background first. So a lot of people are doing scans on internet. So there are many purposes. Some people do it for research work. So we saw some work this year in TMA that we are doing this. Sometimes they use famous tools like ZMAP or Mascan. Other people do it for defense purposes. So let's say, for example, one company asks you to test a network, and then you want to do some scanning to find vulnerabilities or weak systems and so on. Or you can also do it for offense when you want to acquire information on a target and you want to get like weak machines. So consequently, there was a lot of work on detection and scan analysis. So we present a quick state of the art of scan analysis work existing. So the two first papers were papers that use the DShield repository. So DShield repository is like it's a worldwide collected firewall logs, and they are merged in the single place. And so you can get like some kind of worldwide information about scans. So those are mostly like snapshots in time around the beginning of the 2000s. And they look at categories like types of scan, service targeted, and so on. And they also look a bit into scanners, which in this paper we call scanners like the scanning AP, so it's basically the source of the scan. And then there are like the two other references that I'm going to explain a bit more. So the first one is longitudinal work where they used some scans that were monitored in a gateway of a network. So this is a paper from 2007, and so they look at a lot of characteristics of scan and scanners, and the main purpose of this paper, from what I understood, is basically to tell the rise of scanning from almost no scanning to something that is completely pervasive on the internet. And then the last work that I quote here is the work by the people in University in Michigan, where they use some network telescope data to get some information about scanning occurring on the internet. So they look at interesting things like the ports that are targeted. They have something about the AS where the scan originates from. They use the fingerprint of the mass scanning tool to find who is using those tools, and if those tools are used. They also look at the packet rate, and they go into a bit into if they can identify some entities that are doing this scanning. So this is from the point of view of the analysis. So there is only one work on the longitudinal evolution, and now it's almost 10 years old. And there is limited analysis of the behavior of the scanners. So we really wanted to update on the existing work with something more new. So yeah, that's basically what we did. And we have like three main findings. So we have some findings on the scanning evolutions, recent scanning evolutions, some things on the temporal and spatial structure of what scanners are doing, and finally a bit of analysis of the scanning entities that we found in the data and how they address the whole ethic consideration. So a bit of background on data that we use. So we use the Maui traffic repository, which is captured in Japan. So it's publicly available, it's anonymized. So it's captured on the transit link between Japan and the USA. It's been captured since 2000 and it's still going on. And actually inside there is like two main, so it's basically everything is captured on the same particular point in the network. There is two types. There is one daily 15 minutes trace that everybody can use. And some years they will capture like the longer traces, so they will capture like 20 or 48 or 72 hours of traffic that are consecutive, so you have like a more, let's say, continuous view on the traffic. So on top of this, to extract the scan, we actually use MAUI-Lab, which is a ground truth of network anomalies inside MAUI. So the way it's working is that it's using state-of-the-art anomaly detectors, and then it's building some kind of consensus on top of this, and then you get like a set of anomalies inside the traffic. And then on top of this, to actually get like the nature of the anomaly, we use NAC, which is a taxonomy and a tool for the classification, and we apply this classification on top of the results of MAUI-Lab, and then we can extract the network scans. So this is, now I'm going to present like the trends that we found. So this is an updated figure from the paper from 2007, like the brief history of scanning. So we are here looking at the destination ports that are targeted. So there are two main patterns. The first one is ports that are targeted during the whole dataset. So you can see, like for example, SSH, SMB, or Microsoft SQL Server. So it's basically ports that are always interesting for people, and they basically always scan them. And you can also see like funny things with Telnet recently. So this is linked to the, I guess you all heard about the Mirai stuff and so on. So this is the Mirai stuff that was studied for this dataset in March 2014. So this is kind of interesting because I will talk a bit more later about this. And then there is the second aspect, which is the second pattern, I should say, which is the second increase and then the slow fade. So you can especially see this for here. So this was like an episode where there was a lot of worms and so on, like Blaster and Sasa. So they were using like some kind of vulnerability, and then like the patching was very fast, and then you could see like the decrease of the scanning because there is no interest anymore. So I think those parts are a bit different because I think at some point there was a backdoor in one of the malware, and then they were trying to infect the other malware. So this is not actually a vulnerability, or it's a vulnerability of the malware, so it's a bit different. The second aspect that we try to look at, so to give like a more longitudinal aspect of what the people from Michigan did on the network telescope data, we look at the backbone data and check like a longitudinal aspect of who is using ZMAP and Mascan. So those tools were released at the summer of 2013. I think ZMAP was released a bit like 1 month before Mascan. So as you can see, like there was a bit of increase at the beginning because people were basically testing around it, and after like as people are really starting to use it, it was increasing. So this is log scale, so you need to be careful. So if you want to think in terms of proportion, in terms of the whole scans that we saw, so starting from here, this is like this whole part here is Telnet actually. So you have to imagine that TCP is basically linearly increasing. So TCP here ends up around here, so you can say that ZMAP and Mascan is roughly like 10% of all the scanning that we saw in the trace. Then we wanted to try to understand what are the patterns that are used. So Nmap uses an increasing pattern. It means that when you want to scan a prefix, it will scan the successively increasing destination IP address. But this is very easy to detect if you have like an IDS like Bro, and if you use like fresh random walk on your gateway. So what people are doing is that they use like random patterns that make it more difficult for the IDS to detect what's happening. So there's many references on the kind of random pattern that you can use. Like there's an analysis of a /0 scan performed by a botnet where they use IP address. Then some algorithms use linear congressional generator, like the ZMAP and another paper that was published a bit before. And then Mascan use symmetric cryptography primitive to generate the randomness. So to analyze this, we will use something that was previously proposed, which is a statistical trend test called MineCandle. And this is the result that we get. So here we have two y-axes. One is for the number of scans, and the other one is for the proportion of random scans. Here we split between Telnet and non-Telnet because Telnet are so huge that like the behavior is really impacting everything. So first, if you look at Telnet, so this is a dashed line. You can see that starting in 2013, it's really increasing, but the proportion of randomness is really short. So actually, if you look into the data, most of the telnet scans are just like /24 scans that are performed by the infected host. But if you look at all the scans that are not telnet, you can see that there is, starting in 2012, there is an increase in randomness. Although it's very noisy, but there is clearly a difference between this part and everything here, where the randomness is very small. Okay, so after looking at kind of longitudinal picture of the scanning, we wanted to try to understand how scanners are behaving on a smaller time scale. So what we used here is the DHL traces. So those are like the longer traces, so it's like 24 hours or 72 hours of traffic. So here we look at the 72 hours of traffic, so it's basically 3 days of traffic in 2013, so from here to here. So here, this is one particular IP that was performing scanning. And so this graph represents the time on the x-axis, and then you have the interval time of packet on the y-axis. So each dot, like the x-axis gives you the position when the packet arrives, and the y-axis gives you the time until the next packet arrives. So what you can see here is that you have a lot of points located here, around 2 or 3 seconds. So basically you have, if you look at the data, you have like 2 packets that target the same destination IP address. And then you have like a bigger point just after, that is like a couple of 100 seconds later. So what's actually happening is that the scanner is sending 2 packets to every destination, and then it's waiting a couple of 100 seconds until the next destination IP address. So if you look at the data inside, actually all the scans are towards Samba on port 445, and every time all packets are inside the same prefix. So what you have here is that you have actually like 4 scans. And if you look a bit at the data, you can see that they are like super periodic, right? But it's every time at 9 a.m. or 10 a.m. it's starting. And we define here, we say that this scanner is having a very specific activity at this time, and we call this an activity period. So the idea is that we want to extract this kind of activity period, which are different group of scans that are very consistent characteristics. So we define different type of activity period. So the first one that we define is the curious one. So the idea of the principle of the curious is that they will always go to the same destination prefix, but they will target different destination IP address inside the same prefix. So here, I try to make a shim to explain this. Like the shade of the color represent the IP address. So if you have a different shade of color, it's like a different IP address. If it's a green, it's still in the same prefix. So here you can see that it's always going to like the green prefix, but every time it's going to a different shade of green, which means it's a different destination IP address. So for scanner 1, it's actually performing like a curious activity period with 3 scans. For scanner 2, it's actually a revisitor, and the meaning of the revisitor is that it's always going to the same destination prefix, but it's always going back to the same IP address, actually. So it's basically always performing the same scan again and again. So this scanner 2 is a good example, so you can see that it's going to the green prefix and again to the green prefix. Then we have scanner 3, which is performing an explorer activity period. So the idea of explorer is that it's going to target like unrelated destination prefix. And you can see this for scanner 3, so it's going to the green prefix and then the blue prefix. And then finally, sometimes we have some noise with some isolated scans, so we call them isolated activity periods. So in terms of intuition, like the curious are really people that try to get some information on a network, and then they wait a bit, and then they try to increase their knowledge on the network by going back to do some scanning. And the revisitor, from the point of view of somebody who is monitoring a network, is a bit more scary, because they actually want to understand the dynamic of your network. So they will scan you a first time, then they will wait some time and scan again to see if there is a difference or to update their knowledge on the network. And finally, explorer, we guess that are just people that want to get some network a bit randomly. So in terms of data, we use the kind of long traces from the MAUI dataset with several days for 2012, 2013, and 2014 and 2015. So again, we split the telnet and the non-telnet because telnet was so big. And so those are the percentages. So what's interesting to see in terms of trend is that you can see that the curious are increasing from 2012 to 2015. And you can also see that the revisitors are actually decreasing on the same time frame. So for isolated and explorer, it's a bit strange because there is not so many trends, so we cannot conclude anything. So inside the paper, we looked a bit more at the characteristic of the different activity period. And so one interesting thing is that we noticed that the revisitors are much more periodic than all the other type of activity period. And this again shows that people that perform revisitor activity period are really interested in having like a snapshot of whatever is happening on your network and at regular periodic interval. So after understanding like the behavior of the scanner, we try to dig a bit more into the scanner and trying to understand who are the people performing those scans. So we found some high-profile users, like people in Michigan that created the ZenMap. We also find people in TUM that are in the room. We also find some like security company, like Shodan, Shadow Server, or Relata Security that are in the creator of Mascam. And as we showed before, we know that there is an increase in ZenMap and Mascam. So we really wanted to understand what those people are actually doing in the network, and whether there are some like unknown people that are performing some scans. So the way we did it is that we used the fingerprint for ZenMap and Mascam. And we also check inside the DNS PTR record for the source IP. We check for like keywords like probe or probing or scanner and so on. And finally, we try to enumerate the scanner using a DNS recon tool called Fierce. And in the end, we found 18 entities. So we made a huge table in the paper. It's like not so interesting to show here, but you can check if you want. So overall, it's very important to understand that, okay, we found 18 entities, but it's like a very small proportion of whoever is scanning on the data. So in terms of scan, it's like less than 0.5% of all the scans that we found, and it's like a 0.1% of all the scanning IPs. For ZMAP, it's like 25. So for ZMAP and Mascan, it's basically a bit more, but still, it's like less than a third of everything that we found. So there is a lot of people that we were not able to identify, basically. So then, after identifying all those entities, we wanted to try to understand a bit what were the ethical aspect of scanning, and if those entities were actually respecting the ethical aspect for entities, well, following ethical consideration, or performing ethical consideration. So a bit of background. So the main background for ethics in information and communication technology is the Menlo report, which was inspired by the Belmont report, which is a report about medical experiments. So the idea of the Menlo report is to define ethical principles for ICT research. And there are 4 main principles. The first one is that you need to respect the person. So you need to have like an informed consent from everybody, and you need to provide an opt-out mechanism for people to basically leave your experiment. The second aspect that is described in Menlo report is beneficence. So it's basically the trade-off between the harm that you are doing with your experiments and the contribution to the community. The justice aspect means that you need to be fair among all the people that are impacted by your experiments. And the respect of law and public interest principle is linked to the respect of legal aspects and the transparency of whatever you are doing. So the people in University of Michigan, they actually translated those different principles into what should be done when you are performing scans with ZenMap, but this is also transposable for anybody who is doing scanning. So the first thing is that you need to be nice with your sysadmin, because otherwise maybe you won't want to work with you. You need to not overwhelm your upstream with too much traffic, because otherwise, again, maybe they don't want to provide you the service later. You need to don't send too much traffic than what you actually need, because otherwise you will overload the target of your probing. If possible, you should scan slowly from multiple sources. So basically perform a distributed scan. And finally, the 2 aspects that we actually address in this work. is that you need to document your activity in a web page. So provide the IP, the DNS record, and so on, and the scope and the goal of what you're doing. And you also need to provide output. So this is the two aspects that we address. Those are the two ones. So here are the results. So basically, in the table, you have like two criteria. So the first one, this is the infrastructure. This is all the IP and DNS PTR record and the web pages. And then we manually analyze the web pages to check if like the information is actually available. So as you can see, like a lot of people actually provide PTR on website, but not majority. So some people they provide PTR on website for some pages, but some IP, but not all of them. Some provide PTR, but no website, and some provide website, but no PTR. So in terms of the information provided inside the web page, so some like provide everything. So they provide an email contact that you can contact the people that are performing the scans. They provide an opt-out mean. They actually say on the web page, you can opt out from this experiment. Please contact us if you want to do so. And they provide the IP address and the prefix that they use for scanning. And this is done in order for like the sysadmin, if they actually don't want to contact you, or if you are not answering their email, they can just block your traffic using the IP or the prefix. So again, some people did it very well. And then you have like strange things. So people sometimes provide email and opt out, but they don't provide the IP or the prefix. Or sometimes they only provide the email. Sometimes they only provide the opt out, but not any contact information or email. So overall, we found that 7 entities out of the 39, or out of the 18, were actually doing the job correctly. So this is like 39%. So this is like summary of our findings. So we show that scanning is changing. So there is the rise of the internet-wide probing tools, and we also saw like the increase of the random scanning. We provide a classification of the scanner on the way they perform the scanning, and this is interesting for sysadmin because they can assess a kind of dangerosity of the scanner. For example, if they are performing repeated scanning on your prefix at repeated interval and many times, you can guess that there may be some more danger for your entity. And finally, we show that the documentation of the scanning that is performed by entities is not perfect and need to be improved. Thank you very much.
So I have two questions. Did you look at IPv6 first question, and the second one, did you try to correlate the scanning activity to publications, or is it possible to kind of predict which institution is going to publish?
So first question about IPv6. So this is on IPv4. I look a bit at IPv6. I remember finding some network scan, but not so many, actually. And I guess it's not really surprising. For the publication stuff, so first of all, yeah, okay, so I actually have the table. So this is the full table of whether we found scanning. So like the people in Michigan, they are scanning so much and so many ports that you cannot guess what they are doing. So I think that they published on FTP like last year, but they've been scanning FTP for like 2 or 3 years, I think. So this you cannot guess. And otherwise, no, I cannot. Cambridge, it was a bit funny. I think, yeah, it was Cambridge. Because they actually give the name of the experiment in the DNS PTR record. So the time it was, I think it's NDSS 2016, they did a paper on the fact that some websites refuse your traffic when you are using Tor. So they basically perform a ZMap through Tor. So we saw this traffic because it was actually coming out from a Tor relay, basically. And the name was really special. So we actually could guess, but it was like post-mortem, so we couldn't guess anything. But otherwise, no, we didn't try to correct everything. But we have the port and everything, so. Yeah.
So I'm surprised USC doesn't show up in your list of academic scanners.
Sorry?
I'm surprised USC doesn't show up in your list of academic scanners. Because
Yeah.
we've been scanning since 2006.
Yeah, okay, so I didn't put it in here, but actually this is only TCP scans. So yeah, you're using NCMP, so. But don't worry, you're very visible in the traces. Especially because like the monitoring point is like super close from where you send the traffic, so. Yeah, you got it.
So at IMC 2016, there was a paper about a new TCP scanner named YARP. I think it stands for yelling randomly at a router, something like that.
Okay.
And I was wondering if you considered it in your recent research, or if it's for ongoing work, maybe?
No, we didn't consider it. Do you know their fingerprint or something?
The particularity is that they use a TCP, particular TCP header to be able to have a stateless probing. So they send a probe by editing a header, so they can identify which to which probe it corresponded when they receive the reply.
Okay, yeah, I don't know. We like the only signature I look at is ZMAP and TCP and Mascan. I know that there are other tools with signature, like I think Unicorn has some signature, but we didn't look at those. So yeah, thank you for the pointer. Yeah.
Have you thought about burning one of your IPs to check if opt-out actually works?
If
opt-out really works, but if you send an email, will they really stop scanning?
No, we didn't try. Yeah, that's maybe the next step, I don't know. Yeah.
So what is the slowest scan rate you were looking for or found? Is that?
You mean like from the classification part?
Yeah.
So okay, so there was not really a rate per se. Like the things that we are limited by basically the anomaly detection algorithm. So basically, if it's not detected by the anomaly detection, then that's the
range.
Yeah.
Yeah.
So like the signature is more like you need to have like one source, at least 15 destination, and then there are some like threshold on the flags and so on to ensure that it's actually a scan and not some server communication.
So with 15 destinations, is that, I mean, are there things like BitTorrent where the swarm's gone or the tracker's gone and somebody contacts and gets a bunch of failed connections? Does that trigger, or were there other?
So we actually use like the TCP flag to ensure that there is like some, like we ensure that there is like, for example, a lot of scene and all the other flag needs to be at 0 and so on. So I guess this kind of removes kind of noisy stuff.
Yeah. And so do you have a feeling then, like, what are the stealthy behaviors just based on what you did find with the anomaly detection? Like,
sorry again.
What are the stealthy behaviors? Like, what, you know, things are headed towards being more stealthy. What is it? Just rate reduction, or?
Well, there is the rate reduction stuff, because I did more experiments. I know that for example, like TRW is much more sensitive than the detectors. So we would have found more scans if we use Bro with TRW than just detectors. And there is also the coordinated distributed aspect. So if people use coordinated distributed aspect, if you are lucky, you can catch them. If they use like the /0 paper from Dynoti et al., they basically wake up, send 8 packets, and then sleep for several hours. So you're like, okay. I mean, if you have enough traffic, maybe, but otherwise it's. Yeah.
Do you see anybody moving around where there seems to be some scan going on and then they disappear but re-emerge in a different part of the network later?
Okay, so like the people from Errata Security, they are basically using one IP and then they change from each of their campaign. So
okay.
I don't know if it kind of fits
This
your
kind of
description,
thing, yeah.
maybe. And I know that people from SBA research too, so I put them here, but they are kind of academic too. And I know they changed their IP a long time too. Or because we interacted with them because there was a problem, so I think, yeah, there is only one IP here. I know that previously they used another IP, but maybe we only saw one or something. And even the people from TUM, they directly told me that they use much more IP than what we saw here. So
Okay.
it's just one measurement point, so you don't see everything.
No more questions?